Okay, well, welcome back, everybody. This is week 13 out of 14 for the semester. Today, I don't have any lecture scheduled. It's going to be a review of where people are with their projects. And my hope and strong encouragement is that you all work together to help each other do as effective a job as possible on your projects. I realize that there's a lot of diversity among the projects, but that's a strength in the sense that people can provide feedback. I know we had a rather elaborate form where we asked you to comment on various aspects of each other's projects. Some people did upload that form, some didn't. If you did, please keep filling it out. You don't need to do a separate form for each week, but take the form you already had and try to fill in additional information to help each other, and then submit that. Okay, is that clear? And I think that's the most effective way to go forward with this. So again, this is Engineering 443, 543, 13th week of the semester. It'll be student projects as before. This is being live streamed on YouTube and being recorded. So if you don't want to be visible, let me know and we'll stop that during the presentation. And Josh, I see you're here now, so that's great. And so the purpose of this class and the next one is to help everyone do the best they can in terms of presentation. That could be problems you're having with the software you're developing, ideas you're having, showing how you're documenting or presenting your work, anything that you like in terms of getting ready to have a project that's complete. And I hope that these reviews are useful. And one of the things that this class includes in its grading is student participation. And so one of the key aspects of student participation is helping each other do the best job they can on their projects. So at the moment, we have a roster that looks like this. We have Fonbo and then Kali, Tyler, Devin, Jeffrey, and Drew. And I don't see Devin on the call, so I hope he's okay. So why don't we start with Fonbo and get an update on where you are and how your project is coming together. I know you were already pretty far along, and you're working on writing it up and documenting it. So why don't you give us an update on where you are?
Okay. Yeah, so let me just okay, so mostly for the updating of the slide, I'm just adding some more tasks on to figure out how to, like, why there's a lag inside the Nanohub application. So first I'm trying to run the performance counter in order to calculate the like the running time and also the CPU time and FPS of each of the delay time step. It seems reasonable because if the delay time is very big, for example, 0.1 seconds, the FPS will be very low number because it takes like about 10 images per round. So the FPS is a little bit lower than like a faster sampling rate. And also the CPU time also comes down. Like it takes the most time for like a higher delay time. For the rendering time, I don't know if this second is sampling in millisecond or like or in second?
Yeah, that's in CPU ticks, which is sort of a weird little number. Yeah.
Okay, so it seems for running time, like some number between like 0.1 to 0.001 may give you like a lower running time. So these are all running in the Nanohub. And also I'm trying to run like in my local machine, but but I don't have the correct version of Python. I only have Python 3.8, and it seems Andy only has like the version for 3.7 and 3.9. So I may like install like the correct Python container again and try to run it on locally. But I think when you're running on locally, these things trying to be the same. The only difference I think is all about the queue time. So if I show you a quick demo, I think this is on Nanohub. It's my own code. Okay, I think this is running locally. For this one. So if you can see like running locally, the frame is updating faster, like in a reasonable rate, like in a user reasonable rate. But I think the FPS and running time are most similar to all the like inside the kernel size. But you can see the event queue of the Python here, like the Python 3 kernel here. It will respond immediately after you trying to have some events like inside the widgets. So that's why like you can so that's why if you're trying to move that, it will give you immediate instant feedback like from your like keyboard and mouse events. And if you hit pause, it will immediately interrupt like all the running steps because the queue is transmitting faster when you're running locally, and there's no lag between like your kernel and like the web browser, like the JSON file you have here, the notebook itself. So the connection between the notebook and the kernel is faster, like by the serial MQ like communications. So that's why there's no apparent lag inside it. You can very easily to move and trying to interact with that. But if you switch into the Nanohub application, so this is running on Nanohub, and I think I have a delay time of 0.01 as a default. Yeah, so here, like the delay time sleep is 0.01, which is the same as I have like running locally here. So okay, so this is running on Nanohub. And this is the correct new version. And I'm trying to run the same code as I have. You can see even for the initialization, it takes a little bit longer time than running locally, like the machine. So if you hit run, you can see the particle moves. But when I hit pause, it will gives you like a very longer waiting time. Like if you want to interrupt with the kernel, like the notebook. I think that is because all the things are like transmitting from the notebook and to the Python suite, like IPython kernel has a very huge lag, and the queue inside it accumulates when you hit a run. So that means when you hit a run and then you pause, it will waiting for the simulator to run like the corresponding enough time after you hit a run and before you hit a pause. And after it it completes like all the queue, then it will returns into the pause state so that this pause will turn into like a green light. If you're looking at the performance log, I think it's Windows. So it only has 100 timestamp here. So it has not runs into like 200 timestamps. I think it's really slow. It's still like in the 100 steps.
Fanbel, what was I saying about how Python threading works?
Yes. So here we only have like one background thread, like running frequently, like a background thread, which updating the frame like in 0.01 second for each frame. So the Python threading only can run like one main function, like only run one thread, like at one time. So so the whole application only runs the background thread as its main function. So the background thread takes takes the most of time to update all the frames, other than all the like the main thread which updating like all the information inside it. So
yeah. So the background thread, when the background thread calls the C++ function of time step and render, what the primary thread, its job is there to listen for messages in the event queue. So what is happening to the main thread when that other background Python thread calls into C++ land?
So
is the main thread able to process messages?
no, they will be broke like based on like the internal clock, like what is it called like in Python?
It's called the GIL, the global interpreter lock. Yeah,
the global interpreter clock.
Yeah.
So it cannot like interference all the thread, like the background thread, when the main thread trying to wait for the background thread to complete the task.
Yeah, this is actually a fairly interesting problem, because the normal solution that works everywhere else is when you call into C++ land, you basically make a Python call to release the GIL, and that allows Python to go off and do its own thing. And that's sort of been, the standard way of doing things for a long time. But there is something interesting in Jupyter where when you try and release the GIL in C++ land, it causes the interpreter to crash. And that's true on Mac, Windows, Linux, when it's running in Jupyter Notebook. And I think that's something to do with the 0MQ messaging kernel. I'm not 100% sure. But anyway, the way to go about fixing this, and I'll try and get to this next week or something, is in C++ land. What I'll do is I'll spin up a background thread in C++ land that'll go off and do the render time stepping, and every time that native C++ thread makes a cycle, it'll call back on the main thread and call Fanbo's image handling function. So what that'll allow us to do is leave the main Python thread free to process messages and listen for all of the client-side messages and not get that queuing issue, all while we're doing the actual rendering in a background thread in C++ land. So basically, we make a new function that I'll call like run async that just simply spins up a background thread in C++ land and returns right away.
Yes. Yep. So that is for like next week task, and hopefully we can finish it by the end of this semester.
So let me understand. So the problem is that the Python thread that's processing the interrupts is waiting to complete other things. And so, and what are the tasks that are queuing that are getting you stuck? Is it the actual computation? Is it the rendering? Is it the communication from the server to the local machine? Which are the tasks that are
what's causing it is in Fanbo's background thread. If you set the sleep time in there too low, then that thread is always in C++ land. And if the background thread is in C++ land, the way Python works is that effectively blocks all other threads also. And like I said, the normal technique of releasing the GIL, there is some issue with the Jupyter notebook that causes it to crash the interpreter. And it's weird. I mean, the exact same code runs perfectly fine in the regular Python interpreter, the way it's supposed to, but there's some weird issue with Jupyter Notebook. And so this actually turned out to be a rather interesting research issue.
Boy, that sounds like a major problem with Jupyter.
Yeah. Well, they say that they say that doing native Python threading in Jupyter is not recommended, which this is evidently why.
So they recommend using the C++ workaround, or what are other people who need to do this kind of?
I did some searching on this, and looks like what we're doing is actually relatively new. So I'm not aware of anybody who's doing this sort of interactive application in a Jupyter notebook.
Well, it's too bad that you run into you run into a problem like this, but I guess I'm sure that people on Stack Overflow will be very grateful if you have a solution to it.
Well, the nice thing is this will be nicely documented in the paper that Fanbo and I are working on.
Yeah, so I think it works perfectly when you like run the Jupyter notebook locally.
Mm-hmm.
So the only issue is like when you want to apply it into a Nanohub container,
Mm-hmm.
which runs all the things, it will give you the lag. And I don't know if any like the web browser web browser issue or like your machine issue also affects the performance of connecting with the Nanohub application.
Yeah, I'm not sure.
Yeah, like for example, the internet connection, like the bandwidth of the internet or other relative issues may also affect like when you're running on Nanohub.
Yeah, the internet connection will. Oh, that's actually a good question. I'm not sure if they're using bidirectional sockets for the client server messaging. Yeah, that will definitely affect it.
Yeah, but like as for our project, I think like you can run locally in your machine, like using the Jupyter notebook, other than using terminal. I think it is also like a very good application.
And yeah, and we could run on Jupyter with a little bit of a laggy behavior.
Yeah.
and yeah, I think for the paper that will be really, really nice to show the original version with the laggy behavior, explain what's causing it, and then implement our solution and be able to show them side by side.
Yes. Yeah, so I think that's all the updating I have, and all the other things. I think I'm not doing any modifications. Yeah. So the only modification is from the Nanohub deployment to the tasks.
And
I guess on that one slide, maybe some extra text to explain what the columns and row, what those numbers mean would be helpful.
Yeah. I will add like more detailed like charts here.
Right.
Is there any questions?
I think getting this to run in real time, I mean, doing this kind of real time visualization isn't trivial when you're doing it remote. So I'm impressed that you can get it to work.
Yeah, I think that's also true. Like when you're running the Jupyter on the Google Colab, and the Google Colab also does not like encourage you to use the image widgets, and to like even for the Matplotlib, they do not like, encourage you to run interactively like the Matplotlib inside the Google Colab.
I don't know, last semester when Jeffrey did his project using the Matplotlib 3D plotting, and he had sliders to rotate and pan the images. That ran fast on Nanohub. So, I mean, occasionally if Nanohub was being annoying, it was slow. But in general, you didn't feel a lag between pulling the slider and having the image rotate. And so that's why I was wondering whether the issue was the amount of time it was taking to do the actual rendering of the image, or whether it was the amount of time it was taking to send the image to the local machine, or where the delay was.
Yeah, I think it's all from the background thread we had. So yeah, all the like the performance issue is about our background thread.
But this was I think good starting it in Python, because that allowed us to prototype a solution and get it working, and then when we got the details of it working, then it's a matter of basically taking that same logic and then doing that in a native C++ thread that correctly runs in the background and allows Python to go off and do its own thing and happily.
Again, I was actually a little surprised that Jeffrey's demo last semester worked as well as it did, because I would have expected that the response to the widgets was through Nanohub would be laggier than it was.
Mhm.
On the other hand, the images that he was rendering were much simpler than these.
Mhm.
So the amount of computation per image was lower. And I suspect that the size of the image was also smaller.
Mhm.
Any other comments? People have suggestions? I mean, this project is a wonderful one, but it is a technical project, so it's a little bit different from what everybody else is doing. But it's nice to see such differences of approach.
Yeah.
Thank you. I think that's great. I hope you can get it working. Hope it's been an interesting project. Okay, so let's see who was, I think, on our roster. Who's next on our roster? Kali, were you next on the roster?
Yeah, I think so, because I don't think Devin is here. So let's get started. All right, so when we last left off, I had my dictyostelium initialization running, I had my cyclic AMP model running, and the primary issues lied in the areas of cell differentiation and chemotaxis. So coming into this week, those were the first issues that I sought to solve. And in order to do that, I wanted to include a cell attribute tracking scalar attribute map for internal cyclic AMP concentrations. But I found that in order to make that work, in order to have it show up so I could see what was going on, I had to move my cyclic AMP antimony model from the antimony steppable into the default constraint initial solver steppable, so I could create my scalar attribute map and see what was going on. The problem is, after I did this, I started getting an error after at the 120th time step in my simulation saying that there's too much work, the model's failing to converge, we quit. Which was weird to me because this was the first time I'd ever seen this error. I was able to run this model into the thousands of time steps previously with no issue. So with Dr. Glazier, after doing a bunch of trial and error, testing out different factors of the model, the issue was narrowed down to the relay cells. And if you'll remember, the relay cells are cells which will fire a single cyclic AMP signal and then go flat and not fire again, because there's a refractory period where they don't fire. So the implication here is that something with the relay cells in the model is acting up around the 120th time step. And the obvious next step is to investigate this in Tellurium, where the model can run a little more quickly. Also, another side note that's going to come up later, another issue I faced when I tried testing my model is that it was taking a long time for initialization to occur within Nanohub. Like, I had to wait a while before I finally saw my cell initialization show up. So we go into Tellurium. This is a version of the cyclic AMP model without ammonia inhibition, but which does still contain the cell excitability values for the oscillatory and relay models present in the paper that I'm using. So if we look over to the left, we see that the top graph shows the cyclic AMP and cell refractory concentrations over time for an oscillatory cell, while the bottom shows the relay cell. Now, a couple things to note here. One, the primary difference between an oscillatory cell and a relay cell relies in this variable called the cell excitability. And when the cell, which is normally alpha of tau. So if that value is negative, we see oscillatory behavior. And if it's positive, we see relay behavior. The issue, but you'll notice here, is that both of these models seem to be oscillating, but in different phases. So what's happening, so looking a little deeper, the paper defines baseline cell excitability values for both the oscillatory and the relay cells, but they're both negative. What it uses instead is this ammonia adjusted cell excitability term that is equal to the baseline cell excitability term, plus this other mess of a term that takes into account ammonia concentration. So my thought is the reason we're seeing oscillatory behavior, both the relay and the oscillatory cells, is because without ammonia, both of these models have negative excitability values, so they both have the oscillatory behavior. So I think the idea in this case is that if you do have ammonia, then this term will push the relay cells into the positive excitability range. But aside from that, we're not noticing anything really funky around time step 120. So the blue line here is the cyclic AMP curve. And at time step 120, we see that it's slightly increasing, but it's not such a jarring increase that this should lead to a failure to converge error. Same with the relay cells. So part of me was kind of wondering, I know since these are out of phase, maybe there's something weird going there. So I decided, so with this information that there doesn't seem to be much wrong with the model itself, aside from the fact that they both have negative excitabilities, I decided to go back to my original implementation with the antimony, with implementing the model in the antimony steppable where I had it previously instead of in the constrained steppable. And it worked this time. It would go past the 120th time step. This shouldn't matter. I used the same implementation as in the constrained steppable. And another note is that initialization of the cells occur right away. So there's no lag issue, the model will run. I'm wondering if maybe threading is different between the different steppables, if like previously like different threads were doing different steppables or something. I'm at a loss for this one. I really don't know why the model would work in one steppable but not another. I'll take any ideas people have. So with that, Dr. Glazier, did you want to say something?
No, go ahead. I just didn't know. Maybe. So let me understand the process here. You start out, you moved it because you didn't have the tracking field displayable where it was?
Yeah, for some reason, when I tried to introduce a tracking field in the antimony steppable, it wouldn't show up. But then if I moved it to the constraint steppable, it would show up. But now when I try running this again, maybe Nanohub was being weird that day. Now I can see an internal cyclic AMP field when I run this in the antimony steppable.
Can you show us? Did you have it running? Can you actually show us what you got?
Here. And show.
I'm sorry if you tail chased all that time for. DJ, I mean, I assume you've looked into this. Do you have any idea what's going on?
No, not yet. It's a little perplexing. My current suggestion is to do a bit of investigating to what's actually happening in some of the individual model solutions. But tracking that down, we spent a lot of time working on trying to get a good look at what's going on inside of individual cells, and it's not been straightforward in this case.
Because we had turned off all of the secretion and absorption, so every cell was running an identical model.
Yeah.
And it still crashed at 120. So it wasn't something to do with the interaction with the outside world.
Yeah, so what I end up doing is that I have the same implementation here in the antimony steppable that I had just copy pasted when I moved it all the way up here. I still have the code here, it's just all commented out in case we wanted to like look at that issue again. But now it's here. And then, oh, another side note that I was going to give at the end of my presentation, I did end up adjusting the initialization so this all exists in a bigger field. So hopefully now cells are initialized closer to their target volume, so we have less cell death. The problem with this is that it doesn't start with the model centered at all. So we have to find it. But let's wait for the first 0th time step to happen. Okay, here we go.
I think R, I'm typing I don't remember, it's Control R or just R. It's supposed to reset and center the image. Well, crashed player.
I did Command R because I figured that was probably the equivalent on Mac.
No, because it's on the Nanohub side. So I think it's just
Control R.
TJ, do you remember? Is it just R?
Just
What's
R.
the R. No command.
All platforms, just R.
So here it is. Now we have an initialization that in a 1500 by 1500 space instead of 500 by 500. So now each cell is initialized to an area of 27 and most of the target areas are 30.
So that actually launches pretty quickly then for a fairly big simulation.
And now here, for some reason, I can see like my internal cyclic AMP and internal ammonia tracker fields. But of course, in my antimony separable, I hadn't done anything with them because I was supposed to do them in the constraint separable. So if we click on the internal cyclic AMP, it's not particularly helpful at the moment.
Well, the tracking field shouldn't care where you change the values.
But right now it's all commented out.
Okay.
And though I'm pretty sure just scaled up the model and the number of cells shouldn't be too different, I don't think. I think each time step is taking longer.
Wow, something happened. It's still on 2.
Still on 0. Well, that's the last one it's showing. I don't know which one.
It says monocosep 2 at the bottom. Well, so while we're waiting, what was the ammonia? What was the background ammonia concentration? Because you said if the ammonia level wasn't positive, your relay cells were actually oscillatory.
Yeah.
And so that begs the question then what the typical level of ammonia is. Because if the ammonia is 0, you're going to all the cells oscillate. And so there has to be some minimal level of ammonia for that to prevent that from happening.
Yeah, let me see. Did we not have it here? That might be something, and maybe I forgot to copy over from my other model.
But maybe in the source paper there was.
Yeah, the source paper gave a production value of like 0.001 and a diffusion constant of 15. It didn't say anything about like a starting concentration for ammonia.
Did it show what a typical ammonia level was?
I'd have to go back to the figures to check.
Because in this case, if there's no, all the cells basically are oscillators.
Yeah. Yeah, so this is a code that I need to include. Okay, I'll make a note of that. Okay, so now we're at Monte Carlo step 10. Doesn't look too dramatic.
If you run it locally, how fast or slow is it? As opposed to running it on the Nanohub.
No.
Okay, so you've only run it on Nanohub. That's fine.
I stopped the simulation.
All right.
And then those were my updates for this week. The model running in the Antimony steppable, working in Tellurium, something weird with the ammonia that I need to add, and then the initialization update.
So you showed how many? Let's look at your ODEs for a second again. Do you have the Tellurium version of it, of the model?
Yeah.
Could you show that for a minute? Since we have, I want everybody gets half an hour, so let's not waste, let's not give up on the time. I realize it may be harder for people to comment on each other if they don't, when you were debugging rather than final project.
So here's the model being run without ammonia. Not that. Here, this version of the model does not have ammonia in it.
And they're only the two ODEs. It's just R and C. There are no other parameters.
Nope.
Why would that diverge? Andy, any ideas?
And here's the relay.
Andy, do you have any ideas about a CVOD convergence error?
A CVOD issue?
Charlie, do you have a screenshot of the failure, how it was crashing?
It's hitting the maximum number of iterations
Yeah.
per step.
It's a convergence failure.
Mm-hmm.
But when you put the same model into Tellurium, it doesn't crash.
if it's using the same version of Roadrunner, it should be set up with the same configuration and so forth.
Dr. Glazier, real quick, the Monte Carlo time steps in the CompuCell simulation, does that correspond to this value here, the 200, or the resolution, the 2000?
So you have to set up when you define your SPML, when you load the SPML, you tell it what the time units of Monte Carlo steps to Tellurium time are. And if you set the time step to 1, then 1 unit of time in Tellurium should correspond to 1 Monte Carlo step.
Okay.
How so you're saying it crashes in CompuCell, right?
Yes.
How are you calling what parameters are you calling simulate with?
They don't call it directly. It's wrapped. So they so a simulation step is defined as an input, and then every time that they call for 1 step of simulation, the underlying call is to simulate from 0 to whatever the specified period was.
What controls how many substeps it does?
It's the third argument to simulate. It's start, end, and number of steps.
Right, but in CompuCell you don't specify that number of substeps.
You can. If you don't, then a default value is passed to libRoadrunner.
You know what the default is? How many steps it is?
I think it's set to 2 and lets Roadrunner decide after that.
Because 2 is not a lot. So that
no.
means
That sounds like oh yeah, wow. It should be by how oscillatory your thing is. I would suspect that that number should be a lot higher.
Right, except that it's not crashing when there are big changes, and the time series is right. It's crashing at a time when the value is flat. So let's look at when you load the model string. Kali, when you were doing this, were you using those adjustments to the integrator parameters that we did or not?
No, I wasn't.
Okay, so it's just the bare call.
Yep.
And but in this case, it's not crashing. And do you have an example of the one where it did crash? Can you run the one that did crash?
Yeah, I can run that.
Andy, because we did try changing the integrator parameters. We opened up the tolerance, increased the number of iterations before it crashed, and all of those things. And none of that seemed to make any difference.
Yeah, the far and away the biggest influence for that is how many steps, how many number of individual steps you give to simulate.
Right, but that's not something. But I don't even think we have the option of setting that, do we?
Yes.
It's not given in the manual how to set it.
Yeah, it's set step size. You can specify it by cell type for free floating model. It's there.
Well, but step size, then maybe where. Okay, then step size doesn't mean what I thought it meant. I thought step size was the second argument, which is how much time you run for. Not how many subdivisions of 1 step there are.
Ah, yeah, that's right. Yeah, that's the period of one simulation step that's
Right.
simulated by Roadrunner.
I think maybe this term steps here is the one you were talking about, isn't it?
Yes, thank you.
Yeah, because
Sure.
I mean, basically, when you numerically simulate anything periodic, you need about 12 steps per oscillation.
Right, but we have it set to 40 steps. The period of the oscillator is about 100.
Uh-huh.
And it's actually not the number of steps per oscillation that matters, it's the slope. Because you can't have a huge change in value during one substep.
Uh-huh.
But we've got them subdivided. In fact, they're about 4,000 substeps per oscillation,
Uh-huh.
the way we've got it set.
Yeah, these are to Roadrunner. These are not looking oscillatory. The substepping is so small.
Okay, so I set this back to my original initialization with the antimony in
Okay.
the constraint.
I would urge you to version things so that you don't have to do that.
Yeah.
I know it's sort of a pain to have lots of copies on Nanohub because then you have to download them to your local machine. But it's better to have the copies. So, okay, but let's try that and see what happens. Now, is this on the smaller lattice or still on the bigger lattice?
This is the smaller lattice. Or at least it should be.
Because it ran a lot faster before.
Yeah.
It's interesting that the start function is much slower, but everything else is faster.
Oh, but the XML still has the big simulation. Okay.
Just R on top of that should do it. All right. If it doesn't.
It's because I didn't, the XML file.
Okay, so no, okay, that's what I was saying. It's really important that you save the whole simulation when you change, because this is gonna, that's why it's so slow.
Right.
I would go in and change your XML too, otherwise you're gonna wait forever. And you might also move the number of processors up from 1 to 4. You might even try a higher number of processors and see if
I didn't even realize you're only using 1. I thought I was already using 4.
But I think it's worth taking a little time here while you've got Andy's attention, since he's the expert on Roadrunner convergence errors.
Interesting. And I think I know why.
Okay. So it was only that one cell type that was causing the problem?
We'll see.
It's not a bad idea to screenshot errors when they happen. So you've got the. Although I guess there wasn't the max screenshot crashing. Some people were having the max screenshot crash.
And now it's not crashing.
Can we display the intracellular concentration field? Let's see.
I'm not sure why this hasn't crashed yet.
I think you're not calling the time stepping.
That's what's happening. This is why I need to version things. I'm sorry.
I didn't mean to put you on the spot. I just I thought with Andy on the call, maybe he'd have some insight. That's why it was worth trying to do
That's fine.
Yeah, I mean, about all I can suggest right now is figure out what calls simulate and try and figure out what is the number of steps argument that is passed in.
Well, I think I don't mean, Kali. I guess if trying to rebuild your code in front of everybody isn't fair. So maybe we should go on to somebody else. If you get it working, we could come back to it because it's not fair to you to have to try to do that with everybody looking over your shoulder.
I guess editing code is always harder when people are looking. Yeah, it's fine. We can have someone else go, and then maybe if there's time at the end, I can give an update.
Right. Andy, I don't think it's that. I don't think that's the issue, but we'll see. Okay, TJ, who else did you who did you have somebody else you wanted to see present while you still have time?
I am actually out of time. I need to go for the evening.
Okay.
I can check in with Tyler tomorrow and keep things going. Yeah, he's also made great progress, so not worried about getting things done by any means.
So Tyler, do you want to go next or?
Yeah, sure. I have a brief update.
Great, thank you.
Okay. So start here. Okay, so this is the simple model, the results from my simplified model that I had. Basically just my ODE model running in a single cell with a fixed field value and no cell division. And these were the expected results I wanted to see from my full model. And here is the results from my updated model. This is some new clips. The difference being the last model I showed was completely dependent on the time that I expected the cells to differentiate. And with one line of code being moved, I managed to fix almost all my problems. And one of the lines of code that read the field value for IL2, that was being divided by cell volume. And although it made sense after I removed that division, I managed to get the proper values for the thresholds and everything working properly. So here, I don't have a Monte Carlo step clock, which I should work on adding that. But you'll see when the image looks like these pictures up here, these are pretty much perfectly aligned. So when it looks like this, it's about day 5, but my simulation runs to about day 5.5. And that's important for this part right here, where the last, I think it says 6 to 8 hours, the number of effector cells begins to outnumber the amount of activated cells, like you see here. So this plot here is a plot of the total number of cells of each type. And we see the naive cells here have a more rapid decrease toward the start and then sort of level off around 15, which can be seen here as well. We see the effector cells start to rise toward the 2500 Monte Carlo step mark, which is around day 4.5, a little bit after. We see the same behavior with the total cell count as well. And one thing to note about the ODE values is, so here, this is the expected results I wanted to see, and these match almost identically, but these breaks in the line are due to the cells dividing. So if they didn't divide, this line would reach 40 at the same time. But since the cells divide the way they do, the value gets chopped up into a fraction of like 70% or 50% of the parent cell. So that explains these uneven breaks in the line.
So I have a question. So do the values represent amounts or concentrations?
They are amounts. Wait, no, it's concentrations. It's in molarity.
So in that case, you shouldn't rescale them. They should just be passed without change.
You mean the threshold values?
When you pass the value, when you have the cell divide, if it's a concentration, then the value of the concentration doesn't change during cell division. So each offspring inherits the full number. Because the if I take 1 liter of sugar water and pour it into 2 bottles, the concentration in the bottles isn't different from the original.
Right.
So I think you don't have to readjust when you. I don't think that's why people typically use concentration, because then when you have cell division, you don't have to change the value.
Let me jump in here. So this was an algorithm that was pretty well described in the paper, specifically on introducing stochasticity to how much quantity is passed to each of 2 cells after division.
So it is an amount.
Yes, I believe it's an amount.
Well, no, not it. So the algorithm is Tyler. Correct me if I'm remembering this wrong. The algorithm is to take the initial value in the parent cell, divide it or multiply it by 2, and then within some range, there's stochasticity as to how much of that doubled quantity or concentration is passed to each of the 2 cells.
I think that's close. I think it's the ODE value is multiplied by a number between 0.7 and 1, and then the other cell inherits 2 minus that value. Unless that's the same.
So is the concept that the volume of this, is this because the volume of the 2 and daughter cells is not the same, or is this really just stochasticity of where the chemical winds up?
The latter. So yeah, the amount was between let's see, anywhere from an exact concentration being copied to the child cell, all the way to an additional 30% going to the child cell instead of the parent. Yeah, with the basic assumption that that stochasticity represents spatial heterogeneity during division.
Okay, but if the volume of the daughter cells is the same for each one, then you'd pass, say, 1 plus 0.3 times the value to one and 1 minus 0.3 times the value to the other, so that the sum was 1. That would conserve amount.
Yeah, in this case, they do it with 2 minus a random variable between 0.7 and 1. That's the amount that goes to 1 cell. And then, I'm sorry, that's the multiplier that's used to calculate the concentration that is in one of the cells. And then the random variable is the multiplier that's used to calculate the concentration that goes in the other. So it can be anywhere from 100, or I'm sorry, an even 50-50, all the way to 115 and 85%.
Right. I guess what I'm worried about is that TB goes down at each cell division, or is it meant to do that?
I believe it's meant to do that if it's splitting its value.
I'm not sure. I'm not sure what TB represents.
Its only role really is that to dictate when if the activated cell becomes an effector.
So it doesn't do anything after the.
No.
But you see, each one of those glitches is down rather than up. I would have expected that sometimes when you divide, you get more than your share and sometimes less. And you're always getting less. That's so we should probably look at that algorithm, because if the because there's no that suppose that I have a cell volume of V before the division. The total amount I have is the concentration times that volume. I now want to divide that amount into the two cells, daughter cells. If each one of those has volume 1/2, then the amount that I give would be 1 gets 1 plus epsilon times the amount. 1 gets 1 minus epsilon times the amount. Then I sum it, I have the amount. And so I don't understand why.
I think
Not
that's
sure where that 2 is coming from.
I think that's what's happening here. It's yeah, epsilon times an amount and 2 minus epsilon, where epsilon is between 0.7 and 1.
But what I don't understand why is it's 2. Well, if it's on amount, no, I don't understand why there's a 2. The concentration, if the volumes of the two daughter cells are the same, the concentration of one should be 1 minus epsilon times the previous one. The other one should be 1 plus epsilon times the previous one.
Yeah, they just chose to do 2 minus something instead of 1 minus and 1 plus. It's just a preference towards one cell or the other. There's an asymmetry, between the two resulting cells.
And then
I mean, they could have done the exact same thing, but in the way that you're describing, and it would just be more symmetric.
And I guess the other thing is, if I look at the number of cells in your plot, those seem to agree in general, but that A curve, you have cells appearing and dying.
Those are this rapid, like this vertical line is where they split, where they divide, and then this slow decline is when they become effector cells.
Okay, and they don't show that.
Actually, these plots are the average of 10 simulations, the average numbers of 10 simulations, but the general trend.
Oh, I mean, no, I agree. I just was trying to understand where that was coming from. So, but in your simulation, the divisions are synchronous. Are their cell divisions always at the same time?
Yeah, they're every 480 Monte Carlo steps.
So if they showed more detail, you'd still get the bumps and the spike and then the decay.
I would expect to, yes. And if I were to run my simulation 10 times an average, I would expect to see this.
Well, but if everybody divides at the same time, no matter what, you're going to get that spike at the same time for each one. So when you average, it won't go away. If the cell division times were not all at the same, if everybody didn't divide at the same time, but there was some randomness to when the cells divide, then averaging would get rid of that. So let's sit down and try to. You're very, very close to being done. So I think it would be worth sitting down and trying to nail that in this last one or two.
Okay, that sounds good.
Okay. Did you have more, or was it great? Go ahead.
Yeah, I just had a little bit more. So my next steps, I guess, to get this on Nanohub as a full version. And right now I have a slider that's not working properly to change the initial amount of starting cells. And I'd also like to, they introduce these changes here, this lambda C1 parameter in the cast-based equation, as well as lambda T3. These are changes that they made in their results, and these are the corresponding graphs. And here that I would expect to see when I double lambda C1 in cast space, I would expect to see cells die rapidly since they would reach their cast space threshold much faster. And this lambda T3 being multiplied by 100 causes Tbet to not increase as fast, and therefore no effector cells. The activated cells don't become effector. So those are some more sliders I'd like to add, and also if I could change the frequency of the change of direction of motion, as well as the movement speed, I'd like to do that as well.
Okay. I think one thing just for your documentation, when you say you change a parameter, it's important to explain what the parameter does or means.
Okay.
I mean, here it's okay, but when you say change lambda 3, it's lambda C1, that's not meaningful to anybody who hasn't worked with the model a lot. So what you want to say is we have a parameter that represents the frequency of movement, speed, direction change, or something like that. So try to explain in words what the concept that parameter is associated with it.
All right.
For your presentation. Okay. So
And
basically, you're able to track now their simulation. Did you say this is not working, or are you able to generate these two graphs also?
I'm not able to generate these graphs yet. I don't have these implemented into the steering panel, but right now I'm working on the initial cell population.
Right. What if you just change it by hand? What if you just run it with lambda C1 equal to 0.02?
Do you want me to do that right now?
Sure.
Okay.
It's always better to try them out. I mean, you can always change. You can always change it by hand. Even it's not very, from a user point of view, having to edit the Tellurium isn't optimal. But I mean, the Antimony isn't optimal, but you can do it. Two.
So yeah, this steering panel attribute's not working properly yet, but okay, so I expect to see that change in the number of cells.
If we're able to reproduce their other plot, maybe we can reproduce that one. Let's see, can you refer back to what their plot looked like? You could relabel, one thing you could do is relabel the x-axis of your plots to be days. And so you can scale it if you like. Did it crash or that was the end of the
I
simulation?
think they're dividing. Oh, wait, yes,
No.
it-
Huh.
So I think it was that my the cell that I used to track the data points, maybe it died.
All right, and then
Yeah.
you've been unloading the SPML when the cell dies.
Yeah, I think the I don't think I've been unloading the model, but
I don't know why it would say it has no SPML.
I think we encountered this issue before. When a cell would die in the middle of plotting, it would give me a key error.
Okay. Yeah.
But, um, let's see.
Well, it doesn't look too bad. I mean, that looks pretty close to what you had, but
Yeah, that's. I'm not sure if this increase in the number of activated cells is quite correct, but everything else seems to be trending downward.
and what about the other one that they did? The second one, B.
Yeah, so they.
Let's try that. So far, that doesn't look bad.
Yeah, Tibet seems to be decreasing more and more.
But N and PA are both going to 10, which they get. And T and A are both increasing. A is catching up with T.
And I think the simulation runs for about 3,500. And yeah, effective cells barely get off the ground.
Yeah, I would, if you want to do the comparison, I would rescale your x-axis in your plots to be days.
Okay.
So if one MCS is, if MCS are in minutes, for example, divide by 24 times 60 and label the axis and have the X value be MCS divided by 24 times 60 and then label it in days.
Okay.
Just so that it's more comparable.
Yeah, that would probably look a lot better.
But that seems to agree pretty well with what they've got.
Yeah, so now I just want to work on getting my steering panel set up so I can adjust the model more.
Yeah.
But that's about all the updates I have.
I think that's impressive. I'm glad that you were able to track down that bug that was holding things up. That's good. Anybody else have any comments? Suggestions? Okay, who would like to go next? We used to have
I can go.
Jeffrey. Great, go ahead.
So I still don't have the Nanohub dev account. What I've been doing is just putting text into the into a Jupyter notebook, kind of similar to the design or layout that I used for the project last semester. So it kind of starts out with what I have in these slides with basic fluid dynamics that I showed last time. And then it goes into dissipative particle dynamics and what's used in Mechanica. And I explain these parameters, and that's what people will be able to adjust through the exercises. And what Andy and I talked about is to make notebooks for each of these different simulations, so they aren't so it's easier to reset. And also I think the notebook might be kind of long with everything in it. So that background information that I just gave it is the same for all of them probably. And then I'll start out with the more simpler flow problems like here with Poisson flow, and give some, well, more information than what I have on this slide, but kind of describe it. And they'll be able to adjust the DPT parameters and look at how I calculate viscosity, and they can see how that changes with parameters, and then also what happens when you add an object into the flow. And then go on to the slid-driven cavity. I just included the COMSOL picture because It's reliable and it's pretty similar to this again. And it'll be the same idea for all of the exercises. They change, or all of the different simulations, they change the parameters and see how the flow pattern changes. And what I mentioned here last week with the parameters have to satisfy this condition, and if they don't, they'll be able to see what's wrong with the simulation when it doesn't. And then after that, I go into chemical diffusion. I'm going to make this one a little more complex, but they'll be able to change the diffusion rate between this source and the fluid, and also the fluid itself. Not entirely sure what to do differently with it though, because it's fluid. So then that will be that, and then I'll get into the end one, the final one that combines them all with the fluid flow and the diffusion and the little ball being moved. And that's, really all I have right now. I was trying to get connect to my lab desktop to show the notebook, but I keep getting locked out of it for some reason right now. So I just have these slides with the videos.
So just coming back to slide 10.
Yeah.
The Poiseuille flow. So the red line is the analytic calculation, right?
Yeah.
And the blue is your distribution.
Yeah. It's actually, I think in this picture, it is all of the particles and not just a slice in the plane, because the boundary conditions are periodic. So I don't think it matters whether I take all of the particles or just a slice.
So at the boundaries, are you truncating? So that is your plot actually, is it the plot auto scaled, or are you giving a minimum velocity of 0?
It is auto scaled.
Okay, so that means that you have slip boundary conditions.
No, there should be non-slip.
They're not. The mean velocity at the boundary is not 0.
Mhm.
Look. So if you take if you average the velocity and calculate the velocity versus position for your points, in the middle, more or less, there's something funny going on at the top, because there's some saturation where there's a maximum velocity, which is odd.
Mm.
But if I look at the distribution, it's about evenly above and below my red line. So you can imagine that the average is actually on the red line. But at the boundaries, you have blue points between 0 and 0.75, and none between minus 0.75 and 0. So the average of that distribution cannot be 0.
Yeah.
Which means that you have partial slip boundaries.
Yeah, I think
and that's not surprising because of the algorithm you're using, but you don't have no slip boundaries.
I think this depends on the interaction length of the boundary. Because when you specify the boundary conditions, you can set the interaction length.
Mm-hmm. Yeah.
Well, but if you have a distribution of velocities at the boundary, and I assume this is this is flow parallel to the boundary, because flow perpendicular boundary should in fact be 0. Then in order to have a net velocity of 0 at the boundary, if there's a fluctuation, I have to have some with a negative value. And you don't.
Mm-hmm.
Now, there are a couple of possibilities. Maybe you took the absolute value of the velocity rather than the velocity.
Yeah, I think I might have actually
You measured the speed rather the.
Mm-hmm.
But I mean, when you plot an analytical solution, you have to ask the question: does my distribution reproduce it? And the first thing to do is to plot the average of your blue points and compare it to your analytic solution.
Mm-hmm.
And I can't give you exactly what would happen because I can't average over that point cloud in my head immediately. But in any case, if you see a point cloud like that in the red line that's supposed to be the analytic solution, you can at least ask the question, could the average of the point cloud be the analytic solution? And in the middle, the answer is maybe, although something is screwy at the top because your values are being truncated.
What the red line is not the analytic solution, it's the polynomial fit that I get from these blue dots.
Well, it looks like a quadratic.
Mm-hmm.
So what is the analytic solution? In any case, the polynomial you're using is forcing it to go through the 0 at the two ends, right?
Mm-hmm.
And it doesn't.
Mm-hmm.
Right? The value of the red line is 0 at 0 and 0 at 10. But the average of your blue points is not 0 at 0 and 0 at 10. It's positive.
Mm-hmm.
So there are a couple of things that are worrying. And maybe it's that your blue points aren't being calculated, aren't actually representing the velocity properly. Maybe you're doing an absolute value of it or something else, but you have to figure out what's going on with that.
Mm-hmm.
And then you should be looking at the deviation of the average from the expected value. That's why you do the analytic form that you have in the middle, in the quadratic there. And then in the middle, at large values of velocity, you have to ask what's going on. Is that a plotting error that you have a truncation at value of 1.8? Or is there something in the simulation that's actually truncating the velocities at 1.8?
Yeah, and that happens only sometimes, and it's in this screen. No, it's not a video. And yeah, I need to look into it more, I guess, but it depends on what the parameters are. And there's no clear cause for it at this point.
I mean, there may be something which in Mechanica that sets a speed limit on the particles per time step.
Mm-hmm.
Or if there isn't something of that kind, then it's very surprising that there'd be a hard limit on the maximum velocity.
Yeah.
And so then it's either a plotting problem, which is possible, or when you're calculating the velocity, you're doing something you don't think you're doing.
Mm-hmm.
But the reason you do a simple case like this one is because you know what the answer is supposed to be. And then you have to, when you look at a point cloud, this is something, I'm going over this because it's something that's important for everybody, not just your project. When you're looking at a point cloud like that, you have to ask, does it in fact have the behavior that I would expect? And if things are going to be, if you want the point cloud to average to that red line, then you have to have an equal distribution of points on the up, above, and below it. Mm-hmm. And the first thing is you notice is you don't. There's also something interesting going on if you come off the boundary. For example, look at 2. 0 to 2. At 0, the minimum value of that velocity is 0. At 2, the minimum value of that velocity is above 0. You notice there are no points with the value of 0. It's a small slope, but it comes off. And that's probably because of this the interaction reflection rule you're using. But you're not, you really do need to calculate what the average velocity is at each point and plot it, because you're not getting Poiseuille flow. Similarly, if you look at that flow around the obstacle on the right, and it may be a question of how the box size you're using or the averaging rules you're using. The streamlines are not doing quite what you would expect. They're noisier than you would expect. And you certainly are getting some things where you get the streamlines diverting around the obstacle. But the way they're doing it is not quite what you would expect for flow around an obstacle. And that's another one where there's an analytic solution. And if you have the analytic solution, you should be able to actually compare the flow that you're getting to the analytic solution. And then you should be able to do a plot, which is the deviation at each position of the analytic solution from the calculated solution.
Yeah.
And I mean, the Poiseuille flow is not the most sensitive test for Navier-Stokes solver. On the other hand, if a Navier-Stokes solver doesn't do Poiseuille flow, it's not going to do anything else. Right. And so you need to, it's not that it has to be perfect. In other words, you can accept certain kinds of errors. You could accept that there's a deviation of 5% or 10%. You could accept that there's some problems at the boundaries. But it's critical that you know what they are.
Mm-hmm.
And so I would take I would take the data you have there and analyze it so that you can actually make an explicit statement of what the deviations from the expected behavior are.
Mm-hmm.
And in the case of the blue curve, in the case of the Poiseuille flow, the deviations in the middle are not so bad. The fluctuations are huge, much bigger than I would expect for this number of points. Something is screwy about the calculation, or at least the way the averaging is done. And that's not probably you, that may be Andy rather than you. But this thing is not behaving quite the way you would expect. Not saying it's not useful or interesting, it's not doing what you would expect. But at the boundary conditions are not no slip. And you want to understand what that is. It's actually very hard in any of these particle-based methods to get no slip boundary conditions. When you do fluid dynamics and CompuCell, you have the same kind of problem. It's very hard to do it. And so I'm not expecting it to be perfect, but I would like to know what's going on.
Yeah, I think
with that.
I think that's probably a plotting issue, because what goes on when you set it for no slip boundary conditions, you set the velocity at the boundary, and then basically the deal is in front of that boundary for a boundary layer, you have an interaction potential acting on the objects that hit it in the normal direction, opposing whatever it is. And then if it gets through that and actually collides, if it gets through that and then it actually collides, then it collides backwards.
Yeah, I'm not sure I don't understand the algorithm. Normally what you do is you create a mirror particle on the other side and you have interaction with it. So with the parallel velocity reversed. Because what you're talking about is the fact that the velocity perpendicular to the boundary has to be 0 at the boundary.
Yeah.
Because you're not crossing the boundary. That's fine.
Uh-huh.
But that doesn't guarantee that the parallel velocity is 0. But you're right. If the particle reflects and it has a velocity reverse, then you should see negative velocity, minus velocity.
And I know from my testing that I was seeing negative velocities there. So my guess is there's the plot might be truncated or something.
That's possible. But if it were truncated, you would expect it to have line points all along 0, all the way from 0 to 2, and you don't.
Mm-hmm.
It goes up as I go away from 0.
I mean, it might be. There's just no way to tell without looking.
Right. So you guys need to sit down. And, again, Jeffrey, I can sit with you and go over some of this. I'm happy to do it. But I mean, this is actually the kind of thing that my PhD is in fluid dynamics. Yeah. So, I mean, Poiseuille flow in a pipe seems very simple, but in fact, duplicating it in a solvers is not trivial.
Yeah.
Can you show do you have the animated Poiseuille flow running? Do you have the video of it? Is that right?
This is a fast one.
Yeah, they're moving backwards.
Yeah.
And some of it may also be how you define your boxes when you're doing averaging on the surface.
Mm-hmm.
Yeah, there definitely is negative velocity there.
So then it's important to actually plot the means of the velocity at each position off the boundary so you can know what they look like.
Mm-hmm.
And for the streamline one, my guess is that just the boxes over which you're doing your averaging are too small.
Yeah.
That's why it's so noisy. If you look at the COMSOL result, you see they have pretty big boxes, right? The spatial resolution of the COMSOL result is lower than the spatial resolution of yours.
Okay. Yeah.
And that's making your life a little bit harder because you're getting more local fluctuations.
I had an issue with the grid when I increased the resolution too much. It doesn't pick up particles in the boxes, and I'm not sure why. So I can't increase it by too much.
When you say increase, you mean make the boxes bigger or smaller?
Smaller.
You don't want to make the boxes smaller. You want to make them bigger.
Bigger, yeah.
Okay.
The problem is your boxes are too small, so you're not averaging enough.
Yeah, so it's yeah, because the volume that you're basically integrating over is really small. You're probably picking up a lot of noise, and this is fundamentally a stochastic method.
So either you have to average over a longer time, or you have to have your average over a bigger box. But a stochastic method. I mean, if you have streamlines that start and end, or streamlines that bump into each other, neither of which they're allowed to do, then you know there's something wrong, either with the calculation or with the way you're calculating your streamlines.
Mm-hmm.
And so those are fundamental issues. Where you get to the middle of that vortex, where the velocity at the core of the vortex is zero, at least in the plane direction, then things are harder, because when the velocities are small and you try to calculate a vector off of that, you have a problem.
Mm-hmm.
So you expect to have some kind of divergence near the center of a vortex. But everywhere else, you should be able to get something that looks really, you should really be able to, if you do the boxes the same size as the ones in the COBSOL, it should be smoother.
Mm-hmm.
And then you do a longer temporal average so that you get some better convergence.
Jeffrey, did you ever do the time averaging like we talked about?
Yeah, I have it set up. I haven't gotten pictures from it yet because I can't run it.
Okay. So this is a picture of a snapshot.
Oh yeah.
Okay.
Yeah, it's not even, that's a hard thing to do, because it's not even obvious that it's legitimate to do streamline calculation on a snapshot.
Mm-hmm.
And I'm not sure what it is. I mean, for a snapshot, what's happening? You calculate the vector velocity of each particle independently, and then it tries to come up with some streamlines off of those vectors.
Yeah.
So that's not a meaningful plot.
Mm-hmm.
When if you think about it, what suppose you have a crowd of people milling around, and instantaneously any one person could be moving in any direction, but the crowd has a net velocity. What you're seeing is all the local noise. You might be interested in that, but in this case, you're seeing the local noise and not the mean velocity very well. So yeah, you have to come up. So the best thing to do is to draw a box. You can do particle tracking too, but you draw a box of some size. You calculate the instantaneous velocities of all the particles in the box. You assign a vector value to that box, and then you repeat that over a bunch of times, average the vectors between the time steps. And then after you've done that, you notice actually that the COMSOL is not doing a streamline. It's just doing a local vector. So that would give you exactly what the COMSOL has done. And then when you've done that, if you want to ask it to calculate the streamlines from that, it's okay.
Yeah, and
then you get a smooth result.
Yeah, and I actually created a function specifically to do this called grid, which gives you back a grid, and then at each side you can ask questions like its velocity, its density, and so forth.
So I think it's not that the simulation is wrong. It's not that what you're showing isn't what you calculated, but I think to make it informative, you have to think a little bit more about how to display it. Okay. And I think that'll apply to all of them, not just to this one.
Yeah.
But again, the problem with all of these things is hydrodynamics. Well, I mean, it's like hydrodynamics or biology. If you haven't worked with the underlying system and you don't have a lot of experience with intuition about how things should behave, then it's difficult to know whether to trust or not trust the computer calculation. If the software doesn't crash, then you tend to believe that not the things coming out of it, and so that's it. But you have to think about how to validate it. I think you're at the point where this is working so well. It's important now to be thinking about that. So I guess Drew, you've been very patient. I'm sorry, I didn't mean to cut you off, by the way. Jeffrey, does anybody else have anything to talk to? I think you've developed this very nicely, but I think now presentations. Other people may have comments. Drew, do you want to?
All right. I think I'm just going to share my code instead of a PowerPoint. All right. Can you see this? I think, all right. So for this week, for just a quick update, my, the first thing I did is I have my project up on Nanohub, but I think I need to publish it or something because it's, I don't know. I still got to publish it because the tool doesn't work yet. But as far as what I've actually done in the code, I am working on adding widgets because I actually looking for suggestions on how I should implement widgets, because the whole point of this is that you're supposed to be able to test different substrates and stuff and vascularities of the tumor. And I've actually implemented a steering panel for vascularity, and I'll show how that works. It just kind of waits for me to do a single update. I don't know if I should have like a button that, I don't know, because it seems weird to me because there's run buttons up here for controlling the simulation, and then I also have to control it with a steering panel that can only work while the simulation's running. I don't really know the best way to use one of those.
Yeah, I think that's right. I mean, when it's an initial value, when it's a value that's only used once at start, then I think you're right to have something that basically is like a button that says start.
So I should have a start button. Like,
well, you don't necessarily have. Yeah, well, I mean, when I've done it, I do something like what you did, where you set the value, and then you have, say, a pull-down menu that says start. You could do that because what you have the option of one of the other widget types is a pull-down menu instead of a value set menu, and so you could use that to select which simulation type you want to run. Does the chemotherapy come from inside the tumor, come from the vasculature, from the peritoneal cavity, or something else? And so when you select that, then the simulation leaves the start function and starts running.
Right.
But I don't think there's anything wrong with doing it the way you did, which is it sits there until you select some vascularity and then does it.
Okay. And yeah, so
but then changing it later won't do anything. So you have to explain to the user that that's how it works. Also,
is there a way to have the steering panel show up in the start? Because normally I have the code that creates these veins through the tumor in the start function, but I had to move it down to the first step frame because the steering panel wouldn't load in time for me to choose a value.
I think I think you may be stuck. In other words, you may have to basically hand implement a start function the way you did it.
All right.
I'd have to look when I played with it, but I'm pretty sure that I had to do the same thing.
Okay. And yeah, so I just need to add a like a drop down to choose between the different sort of substrates, and those will change all the settings so that whenever I have this on Nanohub, people can look at the different models and control the vascularity.
And how is it working? Are you seeing something similar to what they got now, or is it?
Yeah, I'm still Yeah, I'm still getting something similar to what they got, but the problem is I'm still not getting exactly the same values. I still have to look at what's going on there. I might, I don't know, set up another meeting this week just to make sure, because it's similar but not exactly what they had whenever I run the simulations.
If you hit run now, what happens?
If I hit run now, it goes too fast. I'll show the diffusion. It's supposed to work a lot slower, and it's like I'm getting the same sort of acceleration of like the same slope in the plot. It's just happens on a time scale. It's too fast, and I'm getting the same sort of end values too.
So the molecular concentrations are right, but the time is diffusion time is too fast.
Yeah.
So maybe one Monte Carlo step actually represents a minute or an hour instead of a second or something else. Maybe that's maybe it's a time conversion problem for your Monte Carlo step.
Yeah, I think it's a matter of sort of just guessing the values, some of the values they used, because not every number was specified in the paper. So I'm just kind of working on nailing that down. But I think those are the main things I'm working on.
Well, what can we do to help get that wrapped up? Because you've got the simulation part of it working quite well, I think. At this point.
Yeah. I don't know. I'm just looking for whatever else suggestions anyone has.
Well, so then maybe we should actually ask people.
You muted yourself, James.
Kali, I was going to say, maybe you could ask, do you understand what Drew's doing? And can you ask him a question or two that might help him clarify what the model is about and how to present it?
Let's see. So you want to use different substrates, right? Okay. So when you say the cisplatin accumulation, that's just is that like an average value over all the cells?
Yes. Each of these dots is like all the cells. I don't know if I should plot all of them, but the yellow line is the average uptake of cisplatin in all the cells.
Okay, I'm not 100% sure if that's the most useful metric, because if I'm looking at your scalar tracking field, it looks like there's a gradient going on.
Mm-hmm.
So if this accumulation graph is useful for you making the model, that's great. But for me as a viewer, it's like, okay, I guess accumulation is increasing overall. But I look over to my left and I see this gradient, so I'm really not sure what to make of the linear relationship versus the gradient, especially if that's an average over all these cells doing different things.
I think that's a good point. Especially for chemotherapeutic, the thing you probably care about most is what's the minimum accumulation, because the cells that have the minimum cisplatin level are going to not die, which means your chemotherapy is going to fail.
Mm-hmm.
So maybe instead of plotting the value of all the cells, you could plot the average, the min, and the max. Do you think, Kali, would that be a helpful thing to have?
Yeah, I think that would be more helpful to have for sure. And I like the min and the max to put the context in.
So you'd have 3 lines. Because the average concentration will be determined basically by how your body tolerates the toxicity of the drug. You can't make the chemotherapeutic give a lot of chemotherapy because the patient dies before the tumor does. But the efficacy of the drug is determined by the minimum concentration. And you want that minimum to be as close to the average as possible. And so plotting those 3 lines might be a more effective way. I mean, here you see that they're, or you might want to plot something like, one of the things you could do, it'll be maybe a little bit slower, but could be interesting, is here you have the value for each cell individually. You can plot histograms. CompuCell has a we didn't play with it, but CompuCell, if you go to the Twit menus, there's a histogram function. And you could plot a histogram of the concentrations.
Right. I think we
And
did
that-
do an assignment with those.
And then that'll tell you something about, is because you can't really tell. I mean, you just see that there are dots all the way between 0 and 240. You don't know whether there are a lot of points, a lot of values at 240 and 0, or whether most of them are near the mean. If I look at the gradient, the mean value is somewhere green. And so there are a lot more blue points than there are green points, I think. And so a histogram of that value might be interesting. And you can plot a histogram that resets every time you plot it, so you can see how it changes in time. And that would show you the min and the max as well as the mean. So you might want to think about plotting histograms of those concentrations as well as the mean value. So maybe a mean value on one plot and a histogram on the other. But I agree with you, Kali. I wasn't unsure how to interpret that the blue points. And the mean may not be the most informative thing. All right. Any other suggestions for Drew? Can you show just the cell types for that slice, for the same slice? If I add a plot, you could add a plot window.
Yeah.
There you go.
We can show it in 3D.
Oh, but I actually wanted that exact XY16,
Oh,
so I
yeah.
could see the correspondence between the. So the blood vessels basically, in this case, are blocking the cisplatin.
Mm-hmm. Yeah, because this is the intraperitoneal delivery, so it's coming from the outside.
And they're fit pretty well, keeping it out completely in the center of the tumor.
Mm-hmm. I've also, for the sake of, I don't know, time, I have changed some of the properties of this simulation. Normally it'll spread deeper, I think, if I change some of the values. But I mean, it's just running faster right now.
So one thing you might change would be the diffusion constant of the drug. If the diffusion constant of the drug is higher, then it'll penetrate farther into the tumor.
Mm-hmm.
I'm not exactly sure how that would be implemented in a drug, but you can imagine that you could have the drug bound to something that promoted transport. And can you run it with the example where it's sourced from the blood vessels instead of from the
Yes.
intraperitoneum?
If I switch these.
Yeah, so here your number of blue cells is smaller. So it looks like for this particular level of vascularity and diffusion rates, diffusion lengths, the vascular delivery is more efficient.
Yeah, I think that's actually, I hadn't thought about plotting the minimum instead. That's a good point.
Well, the minimum, the minimum maps, the minimum may not be informative, because if you're forcing the value to 0, the minimum is always going to be 0. So what may be more informative is something like the 95th percentile or something like that, which is again a good reason to plot the histograms.
Hmm.
Do you have the code? Do you have the code running?
Here?
You have the. How are you plotting all those points? The point values.
Here they are.
All right. So you okay? So you add the point. Okay. So I have to remember. Why don't you try this? Let's just do this very quickly since we've got a few minutes left. Why don't you add a histogram to your plots? That would be histogram of synthesis platinum levels. You just need one, I guess. That's, I guess, it's just platinum.
Hold on. Okay.
And then where we have to go down where you add the individual values. So it would be after line 146, I think. We have to do do the plot, the histogram. And we could probably do 20 bins or something like that. And the one thing you're going to have to do when you go through all your individual ones, you're going to have to create before you do your 130. If you're going to do this every 10, so in line 133, you'll have to create an empty NumPy array. Actually, I think you can just use it as a list. So I think you can just make a list, something like histogram list. Equals blank square.
It's the Python.
Open square, close square bracket. And then you'd have to append, when you're doing your avsysp in lines 142, after line 142, you'd want to append that value to that list.
All right.
cell dict, just the line above 140. There's a closing parenthesis missing in 144.
Oh yeah.
Let's see if that works. It may Gronk because it may need to be a NumPy array. I don't remember. You'd have to, I can look it up. Josh, do you remember? The histogram.
What was the question again?
How we were trying to generate a histogram.
Right. So
And the question is, what do you pass to get to calculate?
you need to pass an array. You need to pass an array.
Not
The
a
array
list.
of values that you want to create the histogram of.
But can that array be? Does it have to be an array or can it be a list?
Yeah, a list. It can of an array of any type, including a list of order tuple.
So let's see what happens when you run it. Let's try. Why did
There it is.
Yeah. See, I think that tells you more than the other one, perhaps.
Yeah.
You can see there are quite a few cells that have not very small. Except wait a sec, the X and the Y axis are backwards, aren't they? Shouldn't the X axis be the cisplatin and the Y axis be the number of cells?
Yeah.
I think you've got your axes labeled backwards. In fact, I'm sure of it.
Mm-hmm.
But beyond that, it seems to work. Yeah, there you go. See, I think that's more informative. You could maybe have a few more bins, but basically that tells you what's going on. So you see there are quite a few cells that basically don't get any of your drug.
Mm-hmm.
And that means that as far as the chemotherapy goes, it wouldn't work. You'd kill half the cells in your tumor just fine, but the rest would survive. So I think, Kali, that was a good suggestion for you. Does anybody else have other comments about possible ways of improving this presentation? Tyler, do you have any comments?
No, I think it's pretty informative right now. Yeah, I can't think of anything right now.
Okay. I guess I was going to say one other thing, which is, Kali, did you want to show anything, or are you still working on the?
I have the error showing now.
Okay, why don't you quickly, let's show that, and then I had something, a general comment, what I could make. Andy, are you still there?
Yeah.
Can you take a look at this CVO there?
Um, yeah, that usually shows up from not having enough steps when you call simulate.
Okay, so let's go to that option setting in the code. So let's make the number of steps 400 instead of, except why would it say 10? Okay. What about the stiff versus not stiff solver?
Okay, I'm not, I mean, self dots. Yeah, I mean, I'm not familiar with what that does.
With what does?
Well, I mean, Roadrunner doesn't have anything like self dot set SBML global options.
That's not the issue though.
Yeah.
The issue is it has a relative tolerance and absolute tolerance and the stiff versus not stiff option for the solver.
Yeah, I would leave the relative and absolute alone. I have no idea what the defaults are, but
Okay, so let's get rid of those. Let's copy 238 and comment it out and create a new 238. And then let's just get rid of relative and absolute and just set steps to 400.
yeah. And I mean, if that's stiff somehow ends up setting the stiff solver, then sounds reasonable.
So what? But let's turn off relative and absolute. So maybe we're messing them up. I don't think so. I think the defaults are much smaller than that. But anyway, just delete. Yeah, and let's leave stiff on and try it one more time. Now, while we're waiting for that to run, I was going to say, I was on a panel last week with some industry people, and the industry people are people who hire modelers. One of them was from Novartis. One of them was from ComSol, and one of them was from Biomath, smaller company. And they were talking about what their ideal hiring candidate was. And somewhat to my surprise, they said that the things that they most want from somebody who's going to do computational biology are experience in a wet laboratory, having actually worked with animals and cells. That was their highest priority. Their second priority was extensive experience in courses in biology and a real interest in biology and ability to conceptualize biological problems. Their third priority was project management experience. They also would like people who actually understood how drug development worked, the pipeline of how you go from lead drugs to approval through clinical trials. And they really like people who have extensive experience talking to clinicians, managers, and biologists. People who know the language of biology and medicine and like it. Those were their priorities. Knowing some computational methodology was a plus, but they said in general they can take biologists and teach them computing, but they cannot take people with computing experience or lack of communication skills and teach those to them. And so that while they need they occasionally need people who are computer jocks, the number of people who are compute heavy versus bio heavy that they need is 10 to 1. And that the single thing they look for the most is the biology commitment and the communication. And that wouldn't have been obvious to me in advance, because the people that they're hiring are actually doing biological simulations of the kind that we did last semester or doing this semester. But they said that that's really the thing that stands out for them, and when they interview people, is the biological experience and commitment. For what it's worth, that's something that maybe comes up. Josh actually did a short hackathon with a follow-up with Takeda Corporation, the pharmaceutical company, working not with one of the people who was on the panel, but one of the people who was referenced on the panel. And so if you're interested in what that experience was like, you might talk to Josh about it. Josh, do you have any comments you want to make about the experience of communicating with Bottino in your project?
Yeah, well, they are usually highly motivated to get students to learn the techniques they use in the drug development pipeline. Mostly because they need to hire people. But yeah, they're usually highly motivated and very, very helpful. And if anyone wants to hear more about the experience, yeah, do reach out and I'll be happy to talk.
That was through the Fields Institute, right?
Right. It was it was a workshop, but that was only for graduate students.
But so the Fields Institute is a mathematics institute at the University of Toronto. It's famous for doing this kind of thing. They also said that having people do internships with them is very helpful. They like that.
Of course.
But they said perhaps the single most important things, well, the two most important things were commitment to understanding biology and a familiarity with biological language and good communication skills. Project, teamwork, of course, maybe not, of course. Teamwork, collaboration are important. But again, the single thing that they all underlined was that the most important thing is the biological understanding and language. And so I thought that was interesting. I think our undergraduate program does that pretty well. And I think that I know that the undergrads here have bring in industrial speakers and work with people from industry through the BMES, I think. And I think that's really important. That's a great experience for people. Again, I don't know if any or of you are interested in industrial careers, but I don't get to be on panels with industry people very often, so it was interesting to me to hear what their priorities were.
Yeah, last year BMES brought in someone from Lilly who was doing pharmacokinetic modeling.
Yeah.
That was pretty cool.
Well, I mean, this year is sort of over, so it's too bad unless they do something over the summer. But with virtual things, it's probably easier to get people because they don't actually have to pay to come. So the guy that Josh worked with from Takeda, Dean Bottino, might be a good invite. and the person that I met, who was the head of this company, let me get his name. Shoot. So Dean Bottino's at Takeda. John Burke is the head of applied biomath. And he might be somebody you could invite. He says he likes coming and interacting with students. He's based in Boston. And he says mainly he works with MIT and Harvard people because of where he is. But he says that his company does a weekly meet and greet with students from Harvard and MIT for recruiting. And I'm sure they'd be happy to do a virtual thing here. Could be a good opportunity. Nick Brunk went to work for a biomodeling company. So he just is finishing his PhD.
I thought Nick went to work at Wolfram.
He's moved on. He's now joined a math bio company.
Hmm.
And I thought somehow it was Applied Biomath. It has a very similar name, but it's not the same one. And then from last year, from this course last year, help. What's the name of, Josh, what's the name of Maria's student, the master student? Right.
No.
Sam Heaps. So he did his master's in experimental bioengineering with Maria. Took this course, and he was hired by a mathematical computational biology consultancy in Pittsburgh. He's based out of Pittsburgh, and so Sam might have some insights too. He might be a good person to go to. Maybe he could talk, or maybe he could get somebody from higher up in his company to talk. So those are some things to think about. Again, without the ability, I can't travel physically. These things are a little bit more difficult in some ways and easier in others. Certainly easier to get a high-end speaker to give a virtual day to us than to have to fly to Indianapolis and spend 3 days doing it. So
Yeah.
but and you don't have to take my word for it. But it was interesting to me to be on a panel and hear what these pharma companies had to say. Again, I don't know if anybody is interested in an industrial career in this area. All right. So coming back to your simulation, changing the number of steps didn't change anything. So it's not that.
Well, then, I mean, my guess is qualitatively that reaction network doesn't look terribly stiff, and you shouldn't have to use the stiff solver. My guess is that somehow I mean, maybe a wonky value is getting set for a concentration or something when simulate is called. I mean, maybe it's going negative. I mean, I don't know.
But, go ahead.
Yeah, but I mean, basically, I mean, looking at the qualitative output of that system, that is not a terribly stiff system. I mean, I run way stiffer systems using the non-stiff solver. So my guess is that there is something odd that is getting stuffed in, before simulate is called.
Yeah, I thought I checked, I thought I went through the code with Kali and looked for that and didn't find anything. But it's easy to overlook those things. So maybe Josh, you and Kali could walk through it and see if there's.
Is
Can help.
there a way you can put some logging statements of whenever you set a value in there?
Well, we commented out every place where we actually overwrite a value. So there were none.
But so what exactly is setting values in the reaction network?
I'm not sure what you mean. You mean initial values?
No. I mean, so you're saying that when you run these networks, each network in each cell is completely independent, and there's no interaction between that network and the outside world.
That's right. We turned it all off.
So there's no diffusion, no transport, no anything.
Cell.spml.cyclic AMP square bracket value square bracket does not show up on the left-hand side of anything except in the initialization.
Okay, so could you show me the error again? I think that's a trappable error. I think you can do a catch on that. So that is a runtime error. Okay. You might try doing this. Do a try catch around when you call simulate. Or try catch, wherever, and then catch that runtime. And then when you do, print out the contents of that state vector.
So
You probably have to give more information than that. Go ahead.
would it be this line that's the try?
If self.timestep_SBML actually calls simulate,
It
then
does.
yeah. Then put a try catch around that line, and then if you catch a runtime error, I don't know how you grab the state vector here, but looks like you know how to do that. And then I would put a catch runtime error there. And then in that catch block, print out the runtime error and print out the do this. I mean, it'll slow your code down nominally. Before you call time step SBML, make a copy of the state vector to something, and then if you catch a runtime error, then dump that state vector copy to the console.
You can't dump anything to the console in Nanohub. Console's not visible.
Well, then go to the out. There's a thing that says output there. Left. Yeah, that's console output.
We'll see. I don't think it'll print to that. I think it directs to the actual console, which is the command line console, which isn't visible. But you can try. In any case, if it works, you could still do something like plot it or dump it to a file. So
yeah, but you could do something. But anyway, so
But I think you've gone too fast in terms of explaining what needs to be done.
Okay, so what I'm saying is, so you have that line there, self.timestep SBML. That evidently calls simulate. So what you want to do is, before you call that line, copy, grab the state vector somehow, and then copy it to another local variable or something. It doesn't matter what. And then if you actually that copy will have to be before the try block, because in the catch block, yeah, so up, yeah, do, I don't know, whatever you want to name it, and then self dot this, self dot that,
There is no state vector, so you'll have to iterate over cells and append.
no, oh, wait a minute,
You'd have to append C and R for each cell. So you'd have to do a 4-cell,
okay,
and then append the value, the cell ID, comma C, cell C, comma R. It's not fair to everybody probably to do this. Now, if the idea is clear, maybe Andy, you and Kali could walk through it, but there is no state vector, because each cell has its own values.
yeah, I get that. So each cell has a Roadrunner object.
That's right.
Yeah, and then each Roadrunner object has a state vector.
Right. But the thing, do you just want you just want to have the scalar values of the argument, of the parameters? I mean, the variables.
Yeah, because what I'm trying to do here is that my guess is there's some wonky value in one of those initial, and by initial conditions, I mean the present state of the present state of one of those cells might have a wonky value in some local chemical amount thingy.
So one thing we could do is simply plot a time series of those values.
That would, you have, how many cells do you have? You have a lot of cells, don't you?
Yeah.
How many? Roughly 50, 100, 1,000. How many?
2,481.
Okay, that's going to be way too many to plot. That plot, yeah, I mean, by way too many, that plot would just look really, really noisy. So what I'm suggesting is, basically make a dictionary, and then go over all of the cells, grab the Roadrunner object out of all the cells, and grab the state vector out of it, and then in that saved dictionary, put a key of the cell ID, and then a value of the state vector for that cell, and then just save that into that local variable. You don't have to do anything with it, and then do try, and then catch, and then if you get a catch, okay, then you want to go back to those saved values and then look at them to see if anything looks wonky. If does that make sense?
Yeah.
Okay.
Yeah, the annoyance is you'll have to iterate over the cells, because you'll have to pull the values out of each cell separately. But you don't necessarily need a dictionary. You could just append, create a list, append a triple of cell ID, comma, SBML of C, comma, SBML of R, if you wanted.
SBML of C of R, what? I'm
That's
not sure.
that it's Andy, you don't that you if you look at how these things are represented, look at line 288 of the code. Cell.sbml.cyclic AMP references the model. Square bracket C represents the value of C in that particular model, the one that belongs to cell.
Cell.
Don't worry about it, Andy.
Okay.
So is that clear enough that you could play with it, Kali?
That's, yeah, I can do that. No,
Okay, and I'm happy to work with you on it separately.
Okay.
And Josh can help out too. Sorry, everybody, that was a little bit of a diversion. Okay, for people who are getting close, congratulations. For people who are having code issues, we'll try to work with you on it. Thank you, everybody, for your patience, and let's try to get these things right. So I hope we could get things wrapped up for next week. I guess if we don't get it next week, then things will go into next week's the last week of classes, right?
Yeah.
Then you have exams. So I'd prefer, for your sakes, to get as much done before exams as possible. Just try to help you get through it. Okay, anything else we need to go over, Josh, before we break?
No, I don't have anything on my list. Just remember to upload
Whatever you have.
Right. Versions of the code into the shared repository so other people can have access to it and look at it and examine it and provide feedback.
Yeah, it's important. I mean, one of the things you'll be graded on is the degree to which you engage with your classmates. So it is that really critical. Even if you don't download everybody's project and run everybody's project, it's important that you download some projects and make some comments. Okay, thank you, everybody. Josh, could you stay on for just 1 minute?
Yeah.
Okay, good night.